Hey everybody, Dave Lindbergh, THD Podcast again. Today we have a guest with us, and we brought Colin Ward, who's based in the Philippines, and of course, as always, Simon Weston to ask the tough technical questions, which Colin's told us he's looking forward to. So today, Colin wants to tell us a bit about tube amplifiers. So Colin, if you'd please go ahead and introduce yourself.
Yeah, hi. So good morning. I'm Colin Ward. I'm originally from the UK. Been in the electronics and audio industry for too long, maybe 20 years plus. And now in my old age, I'm going back to old tech. So I'm currently designing a new tube power amplifier for guitars for Iron Wolf amplifiers in the US. So we can talk a little bit about old tech today.
Hey, so Colin, it's a contract job.
Actually, no. I'm actually a partner in Iron Wolf musical industry, so that's right. What I'm doing. But out here, I'm also doing a lot of contract design and manufacture some products in the speaker area, amplifier area, other areas of electronics. So yeah, we do contract and build, but in this particular one, I'm kind of involved. So I made full disclosure. I'm in that one.
Okay. Good.
So just from my perspective on things on the commercial side of audio, so tubes are, as I know, pretty popular in pro and guitar amps and also hi-fi. Is there any other kind of areas that you find people wanting to use tubes and why?
Yeah, sure. But most of the other main applications are in kind of specialized areas. Still gets used a lot in military communications for various reasons. For example, tubes remain probably the only thing that's totally radiation hard. These don't get affected by electromagnetic pulses.
Right.
But in the commercial
and why
area,
can you explain why that is? I mean, what affects comparing it to like a FET, I guess is what we're talking about, right?
Sure.
Is the alternative.
The main reason is that, these are fundamentally physical mechanical devices. So they're not using junctions and electrons moving around in junctions, whereas all solid state does. So there's nothing to really interfere with here. And these are very simple to understand. Heat something up, get a stream of electrons and control it. So they don't get damaged by electromagnetics.
What does a power amplifier actually do, Colin?
Okay. So an amplifier, so let's start with what an amplifier is, okay? So an amplifier does what it says on the can. It takes a very small signal and makes it into a big one. So for example, the signal out of something like my guitar behind me, it's probably a few hundred millivolts. If you put that into a loudspeaker, it's going to hear nothing. It's not enough to drive it. Okay, so typically to drive in a power amplifier, in an amplifier, if you want 50 watts, you're going to have to put 40 or 50 volts into that speaker. So in essence, you've got to amplify that signal up. Okay, so what's a power amplifier? So really, you can't go from, it's very difficult to go from a very small signal to a very large signal in one jump. So we have really two stages. We have what we call a preamplifier, so you make it a little bit bigger, and then the power amplifier where you make it very big. Okay, so there's two steps, basically both amplifiers.
So the preamplifier thing, then that doesn't have to be a standalone device. That could just be part of an amplifier. Why do we hear about preamplifiers?
Yeah, actually, so yeah, typically it's so in the guitar world, it's part of the signal chain in the amplifier. In the hi-fi world, it's quite common to separate the preamplifier from the power amplifier, so they make them two separate units. But in the signal chain, they're both amplifiers. They're just one is stepping it up a little bit. So why, in a preamplifier, because you're dealing with a very low signal to start with, you have to design it to have very low noise and be able to deal with that signal. In a power amplifier, in the power stage, you're already pushing in a big signal, so you don't have to worry so much about noise and so on. The signal's already very large. Okay.
So that's why in like guitar amps you see some guys customize their tubes so they get kind of a different sound effect. What's that all about?
Yeah. There's a lot of people have different opinions on which tubes sound better. Okay, so part of what we're doing with the iMorph brand is we're combining British heritage. So I'm using the kind of concepts that were used in the original Marshalls and the original Orange amplifiers dating back to the 60s or 50s and 60s. So I'm using that tech. And in the UK, we tended to use power pentodes like this. This is an EL34, it's a power pentode. But if you're an American designer, you would have used things like 6v6, which is the US equivalent of this. So people say that they have different sounds. Okay, so
right.
I know that's
so a tube as a device predates semiconductors. Then the point of it is that was the only way to amplify a signal before semiconductors. Is that right?
Yeah, sure. So I mean, tubes were invented in, I can't remember the exact date, but probably in the 20s, right? The first tube was patented, right? So that was the staple of the electronics industry up until the early to late 60s when Mr. Shockley invented the transistor. Okay.
So a tube is expressly for the purpose of amplifiers?
No, it got used for many things. It got used for rectification. It got used for switching. But clearly, most of the for oscillators, but most of those applications, when you boil it down, are amplifiers, right? So the original ones in the original radio sets, they're for amplifiers, right? And so amplifying RF, amplifying audio, but yes, generally amplification. The first computer.
So my understanding is, say for a FET, I keep using FET, but there's I should say transistor. Then for a transistor, is that you had this concept where it switches on or it switches off. So right. you'd put a signal onto one port and it would just open the gate, and all this power would flow from some source out to where you want it to go. But you could figure out a way to kind of use it in a smaller range where it wasn't completely on or completely off.
Exactly. So, I mean, actually, you're making a good point. The FET is the closest analogy to a tube in the solid state area, because exactly what you said. You have in a FET, you have a channel which you turn on and off with the gate. Okay, and if you modulate the gate, you can control how open the channel is. So a tube, sorry, going back to my English there, a tube is very much the same. So basically in a tube, you have a heater that boils a cathode, and that causes electrons to boil off the cathode, and they get attracted to an anode, which is at a positive voltage. In the middle.
What do you mean by boils a cathode? I mean, there's some vapor going to the tube.
There you boil off electrons so you have a metal cathode, and you heat it up. Literally, you can see in the tubes behind me, they're glowing orange at the top. Or maybe you can't, but
yeah, I got you on the big screen now.
I got it too.
Yeah. So it's kind of hard, but these are on. I'm not going to touch them because they're hot. But literally, you have a cathode, which is I forget which metal they use, but you heat it. You literally heat it up, and that.
How hot?
I'm not sure, but the actual glass envelope's too hot to touch. Okay. If I do, I'll burn my fingers, and I don't intend to do that. Okay. But,
so it's actually it's a vacuum, isn't it? They're called vacuum tubes, is that?
Yeah, it's in a vacuum. So maybe if I share one of my slides with you, maybe I can point something out.
Yeah, go ahead.
Does the cathode run out? Does it boil off eventually?
There you go. Good question. The answer is yes. Okay. Valves. That's one of the downsides of valves, is that they will. Okay. Let me. Sorry to mess you around here. Okay. So here you're looking at a simple circuit of a valve gain stage or a preamplifier. Okay. So in the middle, this is the valve, okay, or the tube. In this case, this is a triode, okay? So it has 3 elements to it. This is the cathode. So what's not shown on here is there's literally an electric heating element under here. Okay?
Right.
So that heats the cathode. The cathode then starts to emit electrons. We call it boiling off electrons.
Mm-hmm.
This is the anode. The anode is connected to a positive voltage, typically several hundred volts, right? So in the preamplifier of my amplifier behind me, the first gain stage, the anode voltage is around 320 volts DC. Okay, so electrons, which are negative, get pulled towards the cathode, towards the anode rather, okay? And then we have this clever little thing in the middle. It's called a grid, okay? This is literally a piece of metal with holes in it, and you apply a negative voltage to that, and that allows you to control the flow. So you can think of this like a faucet, a tap, right? If you open it right up, you get all the water going at once, but you can control it. And that's what the grid does. So we put our audio signal in here, it controls the grid, right? So it modulates the flow of electrons.
What's the C1 and R3 between the cathode and ground? What's the effect of that?
Okay, so good question. This is called, so in this circuit, this is called cathode bias, okay? So basically you have to, you said it earlier, Simon, you have to, so for every tube, there's what's called a load line, and in the middle of that load line is a linear region, which is where you want it to be for an amplifier. And depending on which class of amplifier, you put it at a different point. So you have class A, class B, class AB. So you bias it at a different point. So there are many ways to do that. You could have fixed bias, where basically you just put a voltage here on the grid and hold that bias. So you're trying to control the voltage between the grid and the cathode. This is called cathode bias, okay? So what this, we'll come to the capacitor in a minute. What this resistor does is basically set the bias, and it's basically auto biases because the current, the anode current is flowing through it, okay? It tracks the anode current and basically holds the bias of the valve of the tube at the same point. Okay, so this scheme is also called auto biasing. The capacitor, you don't actually need it, but the capacitor is there for high frequency gain. It basically bypasses the high frequency AC coming down here, and that allows you to boost the gain at high frequency. Okay, so the bigger you make this capacitor, the bigger the lower the roll off and the bigger the high frequency gain.
So the anode is sitting at, you said, like a couple of 100 volts.
Typically, yeah. I mean, it's at least a few hundred. As I said, in the amplifier behind me, the first preamp tube is set at 320 volts DC.
Yep. And then the input signal is not DC blocked or anything. How does that reference itself to ground from R1? Right.
So in this circuit here, it isn't, but it usually is. So for very good reasons. Okay. So in this amp, this is actually called this resistor here is called a grid leak resistor. Right. I don't use that in my design over here. I use, as you just said, capacitive coupling, and you definitely have capacitive coupling between stages because this point here is sat at several hundred volts. And you don't want to put that much DC into any stage. Okay?
So those capacitors have to be tolerate the hundreds of volts then.
Yes, exactly. So you raise a good question. It's other components. So number one, yes, they have to be able to tolerate high voltage. So typically 400 volts DC would be the rating of the cap. Okay. The next thing is that the audio signal is going through them. So they have an influence on the tone and the signal, the audio signal. So the selection of cap there is very important, and is also, again, in the audio world, there are many many opinions and many myths, many discussions, and capacitors is a big one, right? So I tend to use film capacitors, usually metal film capacitors. You definitely
They'd be physically pretty large units.
No, actually they can be very small these days. So I can, hang on one second.
Yeah.
So typically, I don't know if you can see them inside the bag, but those are 400 volt capacitors.
So switch my thing.
Okay.
Okay, I know that style. Yeah. It's all through hole stuff. Is nothing SMT like that?
In a tube amp, it's through hole. It's typically through hole, right? I mean, there's another big argument in tube amps. If you go back to the old days, to the 50s and 60s, there were no PCBs. It was all point-to-point wiring.
Right.
You can, in the guitar world, in the hi-fi world, a lot of people say PCBs are terrible and you should only use them. I'm using a PCB. Okay, so this is, in my amplifier, that's the PCB. Okay.
Do you think that that criticism is valid, or there's no basis for it?
I think there's some basis, but the basis is about build quality, and you can do good build quality on a PCB.
So the criticism would be something like the traces on the circuit board would introduce noise or have other effects.
Things like that, yeah. Things like that.
Okay.
If you talk to the old school guys who are repairing 50s, 60s, early 70s amplifiers, they'll say, "Oh, we don't want to touch PCBs. It's too hard. There's no way to repair them." Well, I don't agree, but that's.
And so get to the meat of it then. The audio experience, let's say subjectively, is there a difference?
Yeah,
right.
Yeah. So this is a good area to go to, right? So even if you go to the hi-fi world, there's a huge school of thought that says, the best amplifiers are tube amplifiers. If you want the real hi-fi experience, it's tube amplifiers. Well, personally, I agree. I love the sound of tube amplifiers. But if you go to a purely measurement perspective, you measure THD, you measure noise floor, SNR, then solid state amplifiers will, even a pretty mediocre one, will beat any tube amplifier on measured performance.
In what respect is those measurement characteristics different? So THD is high. You have harmonics from the.
Yeah, now we're getting to the area. So in a tube amplifier, probably the best made hi-fi one, using every technique you can imagine, the best distortion you're going to end up with is about 1%.
1%, and that'd be at 1 kilohertz, like 1 volt input, or.
Yeah, at the normal measurement points, 1 kilohertz, you're going to get about 1% THD. Why?
And is that THD figure actually relatively independent of frequency?
Relatively, yes. Relatively, yeah. So you got two issues with tube amplifiers. One is, many, but again, if you're comparing to a solid state amplifier, THD, your best hope is to achieve about 1%. I'm sure somebody out there is going to come back and say, no, we can get to 00, whatever. Okay, well, great. But in my experience, 1% is pretty good, right? And then the next thing is frequency response. Okay, you're going to struggle without. Okay, so in a tube amplifier, this brings us to, we're jumping around a little bit, but tubes are fundamentally high impedance devices. Okay. If you think, I guess I can stop sharing screen at some point. But
you can come back if you need to show more.
If you think about these devices physically, we've just described it. You have a stream of electrons going up a glass vacuum to another plate. It's very high impedance because all you've got is the air. It's all going through the air. Okay, so that's great. It has great things for dealing with signals and amplifying them. High impedance is wonderful to a certain extent. The problem is your typical loudspeaker is 8 ohms, 4 ohms, right? So you can't, well, no, that's a lie. You can, but it's very difficult to connect these tubes straight to a loudspeaker. Okay.
So when you're saying impedance, in that case, you're meaning like the output impedance?
Yeah. So you need basically, you need a matching transformer, right? And this is where your next level of problems start. So I don't know if you you can let me try and stop the share.
That's okay. I've got you focused on you, Colin, so you can do your show and tell.
So I don't know if you can see in the amp behind me. This is the output transformer. So this is a big beast.
Right.
This is this weighs about 6-7 kilos, all right? And this is a guitar amplifier. So I'm not trying to do hi-fi here. Basically, in a transformer, an audio output transformer, you've got several problems going on. You've got the whole issue of the magnetics, but you also have lots of parasitic capacitances between the windings, which play havoc with frequency response.
Right.
If you want to get a very good, so in some good high-power tube hi-fi amps, if you want to extend the frequency out to 30, 40 kilohertz, plus or minus 3 dB, you end up with a huge transformer. Lots of iron, lots of copper. You can't just do, in a typical power transformer, you wind a primary and then you wind a secondary on top of it. In an audio output transformer, you can't do that. You have to basically layer it. So you have a quarter of the primary, then the secondary, then primary, then secondary, and to try and get the more layers you have, the lower the parasitic capacitance. So in a hi-fi tube amplifier transformer, they might do 32 layers. So it's very big, huge amounts of iron, expensive.
So the frequency response issue is only at high frequency. Low frequency, you basically go down as low as you want.
At low frequency, you need the more iron you have, the more iron in the core, the lower you can go, right? So that's a trade-off there. At the higher end, it's about parasitic capacitance. So the more windings you have, the lower you can get the parasitic capacitance, right? And this is a black art, right? I designed now I'm going to use the term loosely. I designed the transformers for this amplifier behind me.
Yeah.
Design means that I cut and pasted several things I found on the internet, because it's beyond me. The mathematics is beyond me even on a good day. So I'm not even going to try. And I'm doing a guitar amplifier. So I basically not trying to achieve hi-fi here. In fact, far from it. But to come back to the point, why can't you make, on measured performance, you will never get the same frequency response and you will never get the same distortion, because you have this inherent distortion in these, and then you introduce more distortion in the transformer because of the magnetic effects. Okay, so you never get the same, but people say it sounds better. Why do they say it sounds better? Okay, there's some good reasons for this. The first reason is that tubes themselves, when they distort differently to semiconductors, to solid state. So I can show you that. I don't know if you can see it.
Yeah.
I have my
scope.
Yeah.
We're looking at the scope.
I've got it spotlighted, Colin. Go ahead.
You can see it? Okay.
Yeah.
So basically the lower trace is the input signal, quite small. So the lower trace is on 1 volt per division. The second trace is on 10 volts per division. So basically, the second trace is looking at the output of the preamplifier on this guitar amp, right? I'm not looking at the power amp because I don't want to hear 100 watts of a sine wave right now.
Okay. Yeah.
If you want to hear it, I can give you.
Yep.
Okay. So if you look as I turn up the input, you can see it getting bigger. So you've got two things going on here. I don't know if you can see. Okay,
Yeah,
so
we can
clearly
see.
amplifying, but the phase is shifted a little bit, right?
Actually, go back to, can you just run that level up again to see the phase move?
Yeah, the phase isn't moving, but what you can see is that I turn the level up. What's the top of the waveform, right? So you can see that it's flattening, okay? You can see it flattening.
Yeah.
But look at the bottom. The bottom is still a sine wave, okay?
Yep.
So this is a real inherent characteristic of tubes. And what it is that they are distorting with even harmonics, second, fourth, sixth, right? So that is a much warmer sound. So if I go back to my, can I go back to my slideshow? Because there's a slide on there I can show you.
Yeah, go ahead. Just start sharing again.
I'm trying. Share.
There you go.
Play slideshow. So if we look at this, which I conveniently found on the web this morning, it shows you exactly. So you can see tube distortion starting to flatten at the top. But this is a transistor distortion. It's very harsh. Top and bottom are totally flat, and the edges have gone triangular. So now you've got very harsh, a lot of odd harmonic distortion, and it sounds very, very harsh. Okay, so that's where the warm, the warm sound of tubes comes from, and that's why guitarists love them, and it's why hi-fi guys, because actually your ear likes even harmonic distortion because they're musical, right? They're actually if you bring musical notes together, they're at the same spacing. So if you're listening to 1 kilohertz and the second harmonic's 2 kilohertz, it's 1 octave up. So chords are made that way. So it sounds nice.
So that waveform, the way it clips out on the one side and not the other, is that characteristic of the tube, like starting to limit out on the high voltage side, but not at the low voltage?
Yeah, I mean, we could spend
negative swing kind of thing.
Exactly. We could spend another couple of hours explaining why, right? I mean, but then if you go to for guitarists, right, the next thing is, so that's nice. It gives you, so when you're not, it's kind of giving you that very warm guitar sound, and I could plug my guitar in and show you, right?
Please do.
Well, okay, let's try it. And I can't play, but I'm going to, oops, I seem to be pitching the stand up at the same time. Let's give you some level so you can hear the guitar, right?
Yep.
Nice warm sound, right? If I hit it with some more gain, it's still okay, right? This is actually the clean channel of the amplifier. So it's a real nice warm. But if I switch, so here's the next thing. As you push tubes harder and harder, other distortions come in, like the bottom of the waveform starts to distort. So you get a mixture of this nice second, third, and that's again what metal guitarists love it. So here's the clean channel. Now the second channel in this amplifier has hugely more gain. Okay, so when I kick that in, okay, give it some volume. Same chord.
Yeah.
This is your metal. Back to clean. So it has different distortion effects as you wind the gain up. Okay, so that's another difference. Transistors hard clip, and that's it. You can't get this kind of sound. And then you have another element, which is the transformer. When you start to saturate the magnetics in the transformer, it brings in another distortion component, which sounds good too.
Does that kind of imply, let's say, if someone is using a tube amplifier for a hi-fi system for speakers, that to some extent there's that level of distortion throughout the range?
Yeah, it is.
It's not obvious on a waveform on an oscilloscope, but that characteristic carries anyway. Is that valid?
Well, I could wind the frequency up. I've only shown you at 1 kilohertz right now, but we could show it at higher frequencies. But basically, it's the same kind of distortion, right?
Yeah.
So coming back to the point. So they'll never measure as good, but the way they distort, i.e., tube amplifiers distort, and and the harmonics they add to the sound is pleasant to the human ear. So that's so I guess I found this. Where's it gone?
Okay, well that's a lot of detail for a good introduction on tube amps, and I guess part of the point here is like Colin's designing tube amps, but you do a bunch of other design largely related to audio, and you're based in the Philippines.
Yeah.
So I guess what we could do is anybody has any deeper dive questions that they want us to review. Colin's got people coming in that need to talk to him. So let's just table that for today. But like I say, if anybody has any questions about tubes or other things kind of audio related, hit us up in the comments. And if you think you got something that we got wrong, we want to hear about that as well. So I guess thanks to Colin in the Philippines, and thanks to Simon, as always, from Japan. All right. So I guess we'll table that for today. So thanks, everybody, and y'all have a great day. Thank you. Bye-bye.
Thanks, Colin.
See you, everybody.
Yeah.
See you.
Bye.
Bye.